basically orbiting a circular orbit. So we don't really know what's going on there, and that's part of why this project is so interesting, because if you look at this graph, you can also see the very low eccentricity. That sine wave tells you that it's basically eccentric, right? A perfectly circular orbit. And then we also have our stars parameters that we were able to get. So this is a rough plot of how the star would be expected to evolve given its mass. And you can see the system XFS hasn't fully converged on an exact estimate yet, but it is definitely at the part of its life where it's moving upwards and to the left on this plot, basically getting cooler and larger as it becomes a red giant. And it's now in that subgiant branch of just starting it out, and this gives us a lot more details about that star's age and exactly where it is. That gives us a nice, clean estimate of where the system is. And so moving forwards, we can't really say that much from the system because we still know so little about how brown dwarf formation would work, and because we don't have a very large picture. And I was searching in the literature for a conclusive estimate of okay, well, how would this brown dwarf have formed if it's in a circular orbit at such and such a distance and such mass around such and such and a star of such and such an age. We don't really have that data set yet, and so this brown dwarf can be part of that data set as saying, okay, well, here's a brown dwarf that's a period of 6.8 days, and it's in a basically perfectly circular orbit. It's a billion years old, so what does that tell us compared to other brown dwarfs that we can see? So the goal from here is to hunt for other transiting brown dwarfs and see if we can characterize them as well, and eventually produce a data set that we can look at and maybe come to similar conclusions from. And with that, I would just like to say many, many thanks to Dr. Latham, Allison, and Dr. Eastman, in addition to Professor Chen and all of my classmates in Astro 98. And also, this project wouldn't have been possible without access to the Whitman Observatory, so I want to thank everyone at Harvard who makes that available at Harvard and the Smithsonian who makes that available for student use, and also to the teams who worked on ChemCam and Trace. Then we also use data from Tessagaya, and also thanks to everyone who worked on Astro-Image Day, Red Bell, and ExoPass, me too. With that, any questions?
Any questions for this?
Is there any way that you could determine whether this object is more planetary-like or stellar-like without looking at other systems? Like, could you come back with recurring observations on this system to make a determination there? Is there any?
Yeah, so we can guess if we look at the transits in much more detail and are able maybe to see, okay, is there any chromaticity to this transit? Is this brown dwarf producing any light of a redder color than the star? Then we might be able to say, oh, this brown dwarf is possibly fusing, but because it's so, it is at the brown dwarf transition, we don't really know, maybe we could see some infrared, but is that just leftover glow from the formation of the brown dwarf? We can't really say. Yeah. Question?
You said it could be part of a larger data set in the future. How many other brown dwarfs in circular orbits are there going to be?
We have one other brown dwarf that we found and didn't have time to include in this report. So we have at least one, and there are definitely others out there. And as tests and other missions continue to run, we'll eventually hopefully see some more of those.
Yeah. So you measure the mass and radius.
Mm-hmm.
Given the mass, does the radius of the brown dwarf make sense? Given the age from the star?
Yeah. Given the fact that it's the radius being about 0.68 Jupiter masses. I haven't actually checked that yet. That's something that I'm going to do. But it did seem a bit peculiar that it's this compact of an object.
Yeah.
Yeah. This is very strange. So yeah. My guess is that this is possibly just another fact of the fit not being fully converged, and that once we have something more accurate. Yeah. Who knows?
And then do you have an age for the? Okay, there it is. Yeah.
The star's age is about 1 billion years or so. I actually just got I stopped another fit earlier today and didn't have time to put it in this, but it said it was converged 0.99 plus or minus 0.08 or something. So
the brown dwarfs will change their size over time.
Yeah,
this
they'll
one should be
condense and cool, and so we can probably find a model or something of that sort. Yes. Thank you.
Another question. How would you pronounce part of those? tidal circularization targeting of the
Yes, glad you asked. So didn't want to include this in the main talk because Dr. Nathan advised me against it. But this is a rough plot of what the tidal circularization timescale would look like for a ground dwarf of this mass around the star of this mass, using the value that we got by Subject et al. The problem is we don't really know what the Q parameters are for this. People have tossed around 10 to the 5 as a Q parameter for the brown dwarf in the papers I've read. And this brown dwarf is over 80 times as dense as Jupiter. So why are we using the Jupiter tidal dissipation factor for this? But assuming that it's around 10 to the 5 and that the Q of the star is around 10 to the 8, which has more like backing behind it, our tidal circularization timescale is like on the order of like tens of billions of years. So we think that it probably is not tidally circularized. But yeah.
But wait, it is circular.
Yes, it is a circular orbit, but that it's the tidal circularization timescale is longer than the age of the system.
Okay. But couldn't you turn that around and say measured Q? Yeah.
Like, would that necessitate us though, assuming that it has been tidally circularized, and without, yeah.
It's a reasonable hypothesis.
Yeah. No, yeah.
Okay, so let's think kind of.
Yeah.
Good.
Okay. Sorry about that.
Okay, our next student, Amand Kwanya, advisor Roseanne De Stefano, external reader Evan Bauer.
Okay, thank you. So my project was on the outcomes of common envelope evolution on white dwarf binaries and potential considerations for the rates of type 1a supernovae. And my advisor, as Shubham mentioned, was Dr. De Stefano. So you may be wondering, what are common envelopes? So common envelopes form when one star in a multi-body system will overflow its Brochelov, and the Brochelov radius continues to shrink faster than the stellar radius, and this leads to an epoch of unstable mass transfer that occurs on a dynamical time scale, where the envelope then grows to surround the system. So this leads to the common envelope eventually being ejected, as the common envelope leads to drag on the orbits of the stars, thus transferring angular momentum from the stars to the common envelope, also causing an inward spiral of our system, so bringing the stars closer together. So for our paper, we considered the hierarchical triple case of common envelope evolution. And so hierarchical triples are systems with an inner binary and then an outer star forming the outer binary. And so the type of hierarchical triple we considered has a white dwarf inner binary along with an outer red giant or subgiant companion. And such systems are relatively interesting, as they can lead to white dwarf mergers, which can lead to a variety of different interesting outcomes, such as, say, type 1a supernovae. So for our model, we wanted to first generate reasonable covering of our parameter space. So we started out by We started by generating our inner binary, so we considered the larger star M1 in the inner binary to either be a carbon-oxygen or an oxygen-neon-magnesium white dwarf, and we considered the companion to have evolved later as either a helium white dwarf or a less massive carbon-oxygen white dwarf. Then for our outer star, we considered a red giant or subgiant in the mass range of 0.8 to 6 solar masses, and then from there we were able to build a distribution of core masses based on that mass, and then use core mass to find radius. And we sampled for around 1 million systems, and we sampled evenly over the bounds reset. And now for our orbital parameters, we started first by generating our inner binary by sampling evenly over log space for binary systems that merge between 1.5 times 10 to the 5th and 1.5 times 10 to the 25th years. We chose this as this gives us a relatively interesting range of outcomes after common envelope evolution. And the equation for merge time is given as the following. This is the assumption of circular orbits. And this is purely an effect due to gravitational radiation. And then we set our third star to be at the point of Roche lobe filling, so its radius being equal to the Roche lobe radius, and we use that to find A out, which is the outer separation of the star relative to the inner binary. So, how do we compute common envelope evolution? We employed the scatter formalism, which is made by my advisor, Dr. DeStefano, and the scatter formalism uses angular momentum transfer to solve for the end states of common envelope evolution. So putting that together, we get the following equations that relate final orbital separation to initial orbital separation before and after the common envelope. And we also have this Q function equation where the big Q function relates the fraction of mass relevant to each star in the binary. And then little q is a mass ratio of M1 over M2, so the two stars in the binary, while QEC is a core mass to envelope mass ratio. And then all other values are derived based off of real close common envelope systems. And then from there we applied the scatter formalism to both our outer and inner binary. And note that after the common envelope, we're just left with the remaining core mass of the third star. So for the outer binary, we have the following values for Q and QEC, as one would expect. Well, for the inner binary, it's relatively similar, but we do need to consider the fraction of effective total envelope mass that is relevant. So we take this by using our Q function and applying it to the mass of the envelope as a whole, and this gives us some interior envelope mass. And then we treat the more massive star in our inner binary as an effective donor, and we get the following Q and QEC values to plug into our equation. So what kind of outcomes are we looking for from our model? Firstly, we just took the results and saw whether they would merge within a Hubble time, and then compared this to identical binary systems, so basically systems where we removed the third star unless it didn't have any common envelope evolution. And so some possible general outcomes we were looking for were systems that just don't merge in a Hubble time, systems that have a merger between two white dwarfs but are below the Chandrasekhar limit, so they just form a more massive white dwarf, mergers that cause a type 1a supernovae, mergers into a neutron star by an accretion-induced collapse. So we set this based on if one of the two stars was a oxygen neon magnesium white dwarf and they surpassed the Chandrasekhar limit, then they would form a neutron star. Then we had some triple specific outcomes as well we were looking for. So one is where the outer binary falls into the inner binary before the inner binary merges, and this leads to chaos within our system. And we also have cases where we have a secondary merger with the outer binary. So this can either lead to cases where if the initial merger created a white dwarf, that white dwarf can gain more mass, go to a type 1a supernova or an accretion-induced collapse. Whereas if our initial merger was an accretion-induced collapse to begin with, we can have a merger with a neutron star, some of which can form a black hole if it exceeds the TOV limit. So here's a table of the outcomes we found. And so we can see a significant increase in mergers, roughly 3 to 4 times, along with a high number of chaotic systems, and rare occurrences of a secondary merger as well. The most common outcomes being mergers into either a white dwarf or a type 1a supernovae. And even we found a small fraction of systems that form a black hole, which is quite interesting to see. To better visualize this, we have the following plot of outcomes for both the triple and binary case, plotted with total inner binary mass on the x-axis and log initial orbital separation of the inner binary on the y-axis. And the red dots indicate systems that end as accretion-induced collapses, green dots are type 1a supernovae, blue dots are white dwarf mergers that don't exceed the Chandrasekhar limit. And then if you look at the top plot, we have purple points indicating systems that had a secondary merger, and at the very top we see black points as systems that ended in chaos. So we can note that for the triple case, we end up seeing a much wider range of orbital separations that produce some form of interesting result, going from a max of 0.6 to somewhere around 3 for type 1a and that sort of thing, and up to 4 for chaotic systems, which is very interesting to see, I think. And as an idea of when these sort of outcomes are generally happening, we can refer to the following histogram. So this has log time for merger, for a few different outcomes, type 1a supernova, accretion-induced collapses, and merges into higher mass white dwarfs, with our triple case in blue and our binary case in orange. So roughly we can see a pretty significant shift in merge time as a result of common envelope evolution, with this blue dotted line indicates 1 Hubble time. So we can see that for the triple case we get a far greater fraction of systems that merge within 1 Hubble time. So something we can expect to potentially see. So what's the importance of these results? Firstly, it shows the importance of considering triples when we look at the double degenerate channel for type 1a supernovae, amongst other events resulting from white dwarf star merges, and frankly not much work has been done into looking at common envelope evolution of triples, so this is a very interesting work in that regard. And we found that triples that underwent common envelope evolution had far higher rates of mergers and greatly lower times to merge, and common envelope evolution also allowed for binaries with far greater initial separations to merge compared to cases without the third star. So, some potential next steps. Firstly, given the importance of triple systems as we have established, we would like to create a more realistic population synthesis to get a better idea of how triple systems could affect actual observed rates of type 1a supernovae, and further exploration can be done with other types of systems, changing the inner binary components or which star forms the common envelope. Yeah, that's it. Thank you for listening, and any questions?
In the plot where you showed the different kind of potential outcomes, yeah, what determines if it ends in chaos? What is chaos?
So for chaos, we basically just looked at roughly the time to merge for just the outer binary and the inner binary, and saw which would happen first. This is kind of an underestimate of the number of chaotic systems, I'd say. But basically, if the system has not had a merger of its inner binary before the third star falls into it, then we declare it as having ended in chaos. Yeah. Yes.
So are these like the simulations that you're running, are they like parametric evolutions of the triple, or is it like, are you studying or is it like a dynamic simulation? Or what is that?
Yeah, so I don't have the equations up here, but it's not really giving a fully realistic case of stellar evolution for the stars. We basically just, for the third star, for example, we set an upper bound on our core mass based on what its core mass at the end of its evolutionary lifetime would be, and then just sampled between that and some lower bound, and then use that to determine core mass. And from there are like equations that give us the radius of the star as well. But for future work, it would be important to use like more realistic simulations to get stars and orbits. But yeah. Any other questions?
How do you check the numerical data?
What?
How do you check your numerical result of data?
Like compared to like real world data?
Yeah.
So roughly we can see if the effects of the common envelope evolution are relatively realistic, but since so we can see whether the effects that our numerical models are having are what we expect for real post-common envelope systems. There's some known set of real post-common envelope systems, but because our sampling method isn't fully accurate to real world data, we can't do a fully rigorous check of that. Yeah.
Any more questions for Anand? Okay, if not, let's thank Anand. next student, Ariel Farmer, advisor Jason Eastman, external reader Sam Quinn.
Okay, hi everyone, my name is Ariel Firmer. Today I'll be presenting my junior thesis research that I've been working on this semester with Jason Eastman. And our project involved modeling the triple star system TOI 568 using ExoFast. So as I just said, in this project we were interested in studying a single target, TOI 568, using transit data from TESS as well as radial velocity measurements from Minerva. We specifically used ExoFast to extract the best fit model parameters of the system, which helped us determine properties of the system as well as its orbital architecture. So to talk a little bit about ExoFast and what it does, ExoFast is a modeling tool that can help us determine the best fit parameters and uncertainties of the system. So this is just like various properties of the system, such as the mass, the radii, luminosity, temperature of the different bodies involved. We can also fit these models to real-life data that we have. So if we have transit data, we can fit a transit light curve. If we have radial velocity data, we can fit a radial velocity curve. We can also look at the spectral energy distribution of the stars in the system. So this kind of just models the spectra of the star and can tell us a little bit about luminosity and temperature, as well as radii. We can also look at a mist model, which tells us a little bit about the age of the star. So we just see where the star is along its stellar evolution cycle. So we can really extract all of these parameters from the system by modeling it using ExoFast. So before actually applying ExoFast, we first just wanted to dig into the data a little bit and see what the system looked like. So here I just extracted the test data and I fit it to a period of the system that we found on ExoFop of around 10-ish days. So luckily we see that there is a transit there. And immediately you might notice that the transit is sort of this narrow V shape, unlike a bucket shape you might expect. And this indicates that the system likely has this sort of grazing geometry. So whatever is transiting is kind of just barely grazing the star rather than passing in front. This doesn't confirm that it's stellar necessarily, but it does kind of suggest it may be stellar because if you have this this grazing object, if it's like a smaller planet, you wouldn't really see it. So we expect here that this may be a stellar companion, which is massively, very massive and sort of just grazing the system. We then actually note that there's a secondary transit that we observed in the system as well. I took this from ExoFast, but we also did detect this in our initial exploration of the test data. And detecting a secondary transit only really happens when you have stellar systems. When you have a secondary transit, that occurs if you have an object that's passing, when the object passes behind the star, you get this dip, and that only really happens if the object is really, really bright. If it's a planet and it's dimmer, you wouldn't really detect that transit. It's also very likely we'd have a planet that is hot over just a 10-day orbit. So this is all kind of hinting that this may be a false positive system. We're really seeing a stellar companion here rather than a planet. So next we looked into the AO photometry, and this is where it gets a little bit more interesting. So we actually resolved two stars here in the K-band, and these stars were separated by around 0.29 arcseconds. And we knew the parallax of the system, so we were able to measure that semi-major axis to be around 140 AU. And this semi-major axis is way too large to have this 10-day transit. These stars are orbiting each other over like a period of likely hundreds or thousands of years. Later, we were able to actually get masses and calculate a period of around 700 years. But again, even before that, we knew that this 10-day transit was not from these two stars. So that leads us to wonder, well, what is causing this 10-day transit event? We can conclude that there's likely a third body in this system that is causing that transit. So in order to further examine the system, we wanted to look at the radial velocity data. Because we have this much larger star here, the primary star spectrum would dominate the radial velocity data that we obtain. So if we detect a radial velocity signal, then we can say, okay, that transit's happening around that primary star. If we don't detect any radial velocity signal, then we can say, okay, well then the transit must be around the smaller secondary star, and so we're not detecting it. So we wanted to look into radial velocity data from Minerva and from TRACE to determine that. So here is just an exploration of the radial velocity data we have from Minerva. What you're seeing here is a periodogram. So basically what we do is we fit a period to the data, and then we measure how well that period matches our data. So we do like a period of 1 day, 1.1 day, 1.2 days, etc. And then on that y-axis, that's the power, how well the period is matching the data. So here I just have an example of a system that has a known exoplanet, and you can see a really nice spike at the period of that exoplanet, which makes sense because that's the model there gets the data because that's what the period is. Looking at our periodogram, it's just very messy and there's no clear period here, which indicates that the transiting object is not orbiting this primary star, it's orbiting the secondary star. So we finally figured out the architecture of the system. We have this triple star system and these two stars here are eclipsing each other over around 10 days, and then they're actually orbiting this primary star over around 700 years. Another thing I didn't really mention earlier that is also interesting is that we actually do also observe this primary star almost pull on. This is because we observed a rotational velocity of the star around 8 kilometers per second. And I'll just tell you, we also found the star to be quite massive, quite hot. This 8 kilometers per second is much too low for a B star to be rotating. You'd really expect you'd really expect a rotational velocity of like hundreds of kilometers per second. That indicates we're probably seeing it almost pull on, which is just another interesting feature of this system. So we finally determined like the orbital architecture of the system, and now we can finally begin fitting it. So here are the initial transit fittings. I did an exofast. Just some things we can extract from these transits. So looking at this primary transit here, we see that depth, that transit depth, that can tell us about the ratio of the radii between the two stars. We can also tell something again about the inclination that I mentioned earlier. Because it's V-shaped, that indicates where our orbit is inclined slightly. The secondary transit also tells us about that radius ratio, and the timing of that secondary transit tells us a little bit about the eccentricity. Because it's happening around halfway, almost halfway through the orbit, this tells us that our orbit is most likely circular, which is consistent with a 10-day orbit. We can also make a spectral energy distribution using exofast. So we made this fitting from data from all these sources, and from this spectral energy distribution, we can obtain various stellar parameters of the system, such as the luminosity, the temperature, the stellar radius. This spectral energy distribution we see here indicates a system of 3 massive stars. We also make MIST models, which tell us about the age of the stars and where they are along the stellar evolution cycle. So this kind of line here, this is almost like analogous to a Hertzsprung-Russell diagram. It's showing the lifetime of the star, and the points we see are telling us where the 3 stars are along their stellar evolution cycle. So these first 2 are kind of right before that turnoff point. They're still in the main sequence, but this third one we see is a little bit past the turnoff point, so it may have evolved to its red giant phase already. We also extract all these other parameters. I'm not going to go through all of these because there's a lot, but I'll just tell you that the first 2 stars are we believe to be B stars, whereas the third star is an A star, and again I said it's evolved perhaps to its red giant phase. One thing that we want to tighten a bit on this model is the ages. If you'll notice that ages are all like a little bit different, but because this is a balanced system, we would expect those ages to be much closer. So as we continue to model this system, we want to work on tightening the age constraints and seeing if we get more accurate measured ages. We also found planetary parameters, quote planetary because it's actually stellar, so such as the period, we got more accurate measurement for that. We did find that circular eccentricity, and we got an actual measurement for the inclination of around 75 degrees. So in conclusion, this project I was able to characterize and determine the properties of this unique hierarchical triple system, which had these 3 massive stars as well as this rare pull-on orientation. We also demonstrated that these false positive candidates can still be successfully studied, and they still make for compelling targets. This was a really interesting system to study, and it was also really fun to see that we could model a system like this with exofast, which is typically used to model exoplanets, but we can also model this interesting triple system as well. And we hope to eventually shed more light on the orbital architecture and evolutionary history of these stellar systems as well, based on their physical properties. So we extracted so many physical parameters of the system that now we can learn a little bit more about how the system formed and how it will continue to evolve. So that's all. I want to thank Jason Eastman, my advisor, Allison Dillon, and Dave Latham for providing data and input, as well as Sam Quinn, who read over my thesis. So thank you. Does anyone have any questions?
Questions?
Yeah.
Could you go back to when you fit the primary model, or sorry, the model for the primary transit? Yeah. So just visually, the one on the left, it seems like your fit might be a little bit shallow. And I was wondering if like your fit might be pulled up by some of those high outliers in the middle of the transit. So I was wondering, do you know what those outliers are, or whether or not that you should be including in your data?
Yeah, that's an interesting question. Well, one thing that I know can modify what the transit looks like is the dilution factor. So normally, like if you had just like 2 stars orbiting each other, like that transit would be like it would be the actual dip you're seeing. But because we have a much like brighter primary star that's next to it, it's actually diluting the transit value a lot. So we have to like adjust that. And that factors into the depth. Again, this is like also from our initial run, so we want to keep running it to get more accurate. That's just another parameter that modifies it though. Yeah.
When this data is gathered, do you know if there's like any modeling of atmospheric transmission parameters or anything like that? Seems to me that have sensitive the secondary nodes.
Yeah, so this is test data, so it wouldn't have any atmospheric interference, I believe. I suppose the radial velocity could as well, but I will say we know with pretty good certainty that there was no signal detected from radial velocity that indicated. Yeah?
Can you please
return to the actual parameters that you got for the system?
Yeah.
Yeah. Okay, so then is it possible, do you think, that given that this two solar masts are less massive than A and B, is already in seemingly an older stage of life than the more massive stars, that maybe this system is something that formed via like some sort of stellar capture, or is that like,
Yeah.
have you really thought about like why they might be?
Yeah.
If those different ages are like the actual artifact
Yeah.
things that are just an artifact.
Yeah, well, that's a really interesting question. We haven't really delved into like why the system might have formed like that. It's something we hope to do. I will just say though that it's the third star actually that's the oldest
Okay.
in this model, not the second one. It's just because it's a balanced system. It's most likely they're all the same ages, and this is just something that we have to work on. I mean, it would be really interesting if they were all different ages, and then that would also tell us something interesting about the formation of the system. So we want to look more into that. Yeah. Any other questions?
Any more questions about me?
And then what was the hierarchy of the system again? Was it like A and B are orbiting each other? And C is orbiting
Yeah,
both?
sorry, I didn't
Okay.
label it, but like this is like A, and then the bigger one is B, and then the smallest one is C.
Oh, okay.
Is how I. Yeah.
Just a quick question, when considering like, you mentioned like the overall history of the system, are like the effects of like lit-off boson mechanisms like at all relevant to the system or not really?
Yeah, that's a really good question, and that's something that actually that my external reader suggested looking into. So I haven't actually looked into that yet, but it could be possible. We were more just focused on modeling the system in the first place. It ended up being much more complex to model than like an exoplanet system with exoplanets. So that was like the bulk of the project, but we hope to look into that. Any other questions?
And what's the total, so given the mass of A,
Yeah.
what is its lifetime before it?
Yeah, it's a massive B star. So
Yeah.
I don't know off the top of my head, but we found it to be around 8.5 million years old at this point.
Yeah.
Yeah.
I guess what I'm saying is, it's an intriguing system,
Yeah.
because the age you get for C is a gigayear,
Yeah.
but it's really hard to have a star that massive
Yeah.
so long. So
Yeah.
that seems like,
It is interesting.
Yeah.
I feel like that might be a shortcoming of the model because we do want to work on tightening those ages, and hopefully they will all like align more if we like we're gonna try to tighten them and see if the model still works if the ages are all closer. But then if it ends up still staying like that is really interesting. Just phenomenal project.
yeah, I mean, there's more exotic possibilities, like
Yeah.
they didn't form together and they found each other.
Yeah, we're really excited to study that. Yeah. Other questions?
Do you have, I can't really read very well from back here, but yeah, do you have estimates for what their metallicities are?
Oh yes, I do. Yeah, they're like there. I can figure out their
Okay.
but we did guess.
Okay, yeah, I was just looking because if the metallicities are very different, then wait.
No, they're all.
Any more questions for Ariel? Okay, if not, let's thank Ariel. Next to Kobe Chen, advisor Ashley Villa, and external reader Harsh Kumar.
Okay. Hello, everyone. So my project's on the generation of supernova light curve templates. And so historically, supernovae have been classified using spectroscopy. So as seen here, astronomers usually look for signatures of certain elements to classify supernova types. And so while spectroscopy is great at classifying supernova, it tells us like the chemistry of what's going on, it also has some significant disadvantages, namely that it's pretty resource intensive. You need specific instruments to do spectroscopy, long observation times, and it's often difficult to do on dim sources. So this is very relevant due to the upcoming development of a lot of large survey telescopes, like the Vera Rubin Observatory here. So we expect these surveys to find thousands of events every night, and so we can't go, one by one we can't do spectroscopy on every single one of them. And so what we want instead is a way to verify what type of supernovas an event is using photometry. Since photometry is much easier and it's much quicker than spectroscopy, so we need to be able to use photometry to predict how an event will evolve over time, and use that to highlight events that are worth following up. And so to do so, we need to have accurate models of how supernova events evolve over time. And so this is where Extrapol comes in. It's a package that my advisor, Dr. Pilar, has been working on, and that she has had me working on this semester. So Extrapol takes in photometry data all the way up there. So it first uses a Gaussian process to estimate the flux values in between observations. And so a Gaussian process is a non-parametric regression method that assumes the relationship between data points is normally distributed. And so the advantage of that is, since it's non-parametric, it doesn't make any assumptions about the physical properties of the system. And so each color there represents a different energy band, and then each of the points is an observation. And so after that, we can use black body laws to estimate the physical parameters of the system. And then we can also integrate over all the wavelengths to arrive at the bolometric flux. And so why do we care about the bolometric flux? So we expect supernova to behave, we expect supernova of the same type to behave similarly. So I'm sure you all are familiar with how type 1A supernova are all rather similar. And so we're trying to extend this concept. And so the total energy output is a better description for, it better describes the supernova's evolution, since it aggregates all the data points that we have over all the energy bands. And then furthermore, through the bolometric flux, we can also infer, we can make inferences about the physical properties of the system under the assumption of black body laws. And so, however, Extrabol's Gaussian process currently regresses to a mean of 0, which we can improve on by informing it with the template, which is where my work comes in. And so the idea of a template is to tell Extrapol on average what it can expect a supernova to do over time. So we're attempting to find the underlying shape of a supernova-like curve, and then Extrapol can transform it horizontally or vertically to fit onto data. So to do so, I aggregated over 500 supernova events, which had already previously been spectroscopically verified, so we know what type of supernova they are. And so in particular, I was focused on type 1A and type 2 supernova. So type 1A are all, they're famously pretty similar as they occur when a white dwarf, accreting white dwarf's mass goes over the Jenner-Swift-Car limit. And then type 2 supernova are also, they also have characteristic light curves because it's thought that oftentimes the shock wave of a supernova, a type 2 supernova ionizes its outer shell, increasing its opacity and making it dim at a much slower rate than other supernova types. And so I ran these different supernova events through Extrapol and got an estimate for the characteristics of each of the events. And so I then calculated the weighted average over time, weighted by uncertainty, and then I also did a rolling average to smooth out any curves. And then, so from here, I use black body laws to generate the templates, which will be going to Expo, by calculating the flux per unit wavelength that's consistent with our physical properties. And so this is in the form of a two-dimensional array, which tells us how every wavelength will evolve over time. And so the graph on the left is kind of a temporal snapshot of a supernova's spectrum at 3 different times. And then the graph on the right describes how, on average, the different wavelengths evolve over time. And then to test our templates, we randomly removed sequences of 30 days from our observations. And so this is something that we actually see in real life because you can't fixate a telescope on an event for forever. So we're going to have like gaps within our data. And so like we see here, this has like a gap of like 100 days. So extrapol usually performs rather poorly when there's large gaps like this. Like I said before, because of the regression to 0. And so this is where a template comes in to kind of inform extrapol what's going on in the middle. So in our test, we're basically trying to predict what the points are in the middle there that we took out. And so by running the remaining points through extrapol to get a prediction for the points we took out. And then as expected, using a template significantly improved the results of extrapol. So on the right, we have type 1A observed versus predicted templates with a template. And as you can see, the points lie much closer on the diagonal, which is good, and then has a much lower mean squared error. And so same thing with type 2 supernova, much lower mean squared error, and also much closer to the diagonal. And so this, from here, there's still lots of room for improvement. So we can optimize some of the parameters that we use in our generation, and then we can also try adding different parameters or different methods to make our models more complex. And then what's the end goal here is to attempt to classify supernova types. That's the end of my talk. I'd like to thank Professor Chen and Dr. Villar back there for all the guidance they gave me this semester. And that's it.
Question for Cody.
So we've been stuck with a nice modest set of supernova light curve types. As you look at supernova light curves, what they actually look like this time, are you seeing any that don't seem to fit any of the established class, or does that seem to fit into?
Right. So when I was, I guess, creating my models, I only used spectroscopically verified supernovas. I don't think there was anything that's super weird going on. But so I wouldn't say so.
Any other questions for Cody?
Yeah, so with the template, I was just wondering, like, does it actually manage to recover some specific features unique to each supernova light curve, or does it just like give a rough idea of what a light curve like generally looks like, and so it's going to be closer than like
so one weird thing I saw was like the type 1A supernova, like it's like a dip and then a rise again in like the temperature. And so I think it does capture that. Like the peak of the spectrum moves around to like account for that, I think. So yeah, it does it.
Other questions? Okay, now let's thank Cody. Okay, our next student, Adam Bosky, advisor Ashley Villar, external reader Ido Berger.
Hey everybody, my name is Adam, and today I'm going to be talking to you guys about a host property-based machine learning supernova classifier that I've been working on this semester with Professor Ashley Villar. So, why classify supernovae in the first place? Well, supernovae are super important for understanding the universe. They contribute to enrichment, galactic evolution, cosmological measurement, and almost every other part of astrophysics. Unfortunately though, supernovae are not super well constrained. We don't really know the demographics of supernovae all that well, and part of this is a result of the fact that the early lives of supernovae are super important to observe, but pretty difficult to observe. And this is sort of a result of the way in which we look at supernovae. So the way that it works as of right now is we have all these astronomical surveys taking tons of pictures of the night sky every night, and when it sees something that looks like it might be a supernova, it triggers an alert, and this alert then sends the object through some sort of classification pipeline, and if the pipeline says it's interesting, we follow it up. If not, we don't. And right now, only about 1/10 of these alerts are followed up, and this is going to drop to something like 1 out of 500 with the Vera Rubin Observatory, just because we're observing so many supernovae, so many more with Vera Rubin, and we don't have all that many observational resources to allocate to observational follow-up. So, the way in which classification is done was traditionally spectroscopically. This transitioned to photometrically in the last 20 years or so due to the high cost of spectroscopic classifications. The issue with this is that photometric classifications of young supernovae are pretty difficult to get confident classifications. The reason for this is that if we have a young supernova in the sky, we only observe it for a few days, maybe a little bit more, and photometric classification algorithms don't do well with a small amount of information. Luckily though, supernovae are correlated with their environments. In the right figure here, we have the x-axis and y-axis correspond to different properties of the host environments of supernovae, and the colors correspond to different classes of supernovae. As you can see, the orange points and blue points sort of are clustered, and the green scattered throughout are sort of clustered in different locations, implying that we might be able to actually correlate these properties to supernova classes. So our goal is going to be to develop a tool to quickly classify supernovae by making use of these properties. So this is a ton of information to put on a slide, but the rest of the talk is dedicated to just giving you guys an idea of how it works. But this is sort of the pipeline that we made and that we use to classify our supernovae. And let's start with the first part, which is taking these SED observations and inferring host properties from them. So the way that we do this is by using neural networks. Neural networks, in as few words as I can say, is basically a series of connected layers that apply nonlinear transformations to their inputs. They're used to model complex relationships. They're used in a wide array of fields. In this case, what we are doing is we are taking spectroscopic measurements, like this in the top right. We're taking the blue points, we're inputting it into a neural network, and we are producing inferences of the mass, star formation rate, and redshifts of the galaxies that give us those blue data points. And we use Zhao et al. 22's data set to train our neural network and infer these values. And our model does pretty well, which is really exciting. If you look over here in the bottom right figure, the top row, the x-axis corresponds to real values, and the y-axis corresponds to predicted values from our neural network. And therefore, we sort of expect, if our neural network is perfect for all of the points to lie along those black lines. We see that we have a really high density along the black lines. Obviously, it's not perfect, but the shading here is in the log of the count, so it's actually better than just your preliminary look at these results. We do note that the performance with photometric redshifts in the third panel is a little bit worse, and this is sort of a result of like a junk in, junk out phenomenon in which photometric redshifts are just generally pretty uncertain. So of course our neural network is going to struggle to predict them really well. And we also, in the bottom row here, the green are the real observations and the blue are the predicted observations. We see that our neural network is kind of struggling to predict low mass and low SFR bumps. This is probably also a result of photometric redshift errors. So Zhao et al., what they do is they take the photometric or spectroscopic redshifts, input them into some like heavy statistics algorithms, and output these properties. So if we have bad photometric redshifts, then of course we're going to have bad results, and if we take those out, those bumps actually go away. So now let's go on to the classification aspect of our pipeline. So to classify, we use something called a random forest. So random forests are basically collections of decision trees, which are fancy words for a flowchart, basically. So what decision trees do is you give it something, you give it some properties of an object, and it pops out a class. So let's say we have fruit, and we have measurements of, I don't know, length and color. Put it into a random forest, it's going to pop out, it's a banana or it's an apple or something of that sort. In this case, we're inputting the mass, SFR, and redshifts that we used, or that we predicted with our neural networks, and we are popping out the 1A or other type of supernova. And in the top right, we sort of show what's called a confusion matrix, which might be confusing, but the x-axis of a confusion matrix is the predicted label or class, and the y is the true label. So let's say we had a 1A supernova, and we predicted it as being other. We get it wrong, it's going to fall in the bottom left quadrant there. But if we predict it as 1A, it's going to fall in the bottom right. So therefore, we're going to want all of our predictions to be in the bottom right or top left quadrants. We don't see that, but we do see that we perform somewhat comparably to existing classification methods. A little bit worse, and I'll sort of get into why that is on the next slide. Also, I do want to note that the different triangles in these quadrants correspond to the random forest predicting based on the true properties of these host galaxies and the neural network inferred properties. So we see almost identical performance with the different properties, implying that the first half of the pipeline is actually doing really well. In the bottom here, we have a purity versus completeness graph, and I'm going to try to summarize it, but basically completeness is sort of the confidence with which we believe our measurements to be correct. So let's say we have a 0.2 completeness, that's the 20% of our inferences that we are most confident in. And purity is sort of a metric of accuracy in this case. So what we find is that for a 20% completeness, so our top 20% of classifications, we get 100% accuracy on 1A supernovae and 55%, or sorry, 100% purity and 55% for other types of supernovae. And also in the blue and green here, we plot the purity versus completeness for neural networks versus, or for the neural network inferred properties versus the true properties. And we, again, almost perform exactly the same, which is very exciting. So, to summarize and just mention a few future prospects, supernova classification is super important for understanding the underlying physics behind supernovae and the universe. We built a host-based machine learning pipeline to classify supernovae. We're not quite at cutting-edge accuracy yet, but our data set actually happens to be pretty imbalanced, so there are way more 1A supernovae than others, and pretty small. So we're looking to sort of improve that performance with a more robust data set from the Pan-STARRS catalog. And another thing, nice fun tidbit, is that we actually get galaxy characteristics out of our classification pipeline, which is pretty exciting and just sort of a nice thing to have. And finally, improved performance would make this tool effective at identifying anomalous and interesting supernovae, which would be great for observational follow-up. Finally, just want to thank Professor Villard so much for the semester. Learned so much about machine learning, astrophysics, and life. Professor Chen, thank you so much for everything. Professor Berger, thank you for being a good external reviewer. Alex, thanks for all my questions that you answered. And then classmates, thanks.
Question 5.
Yeah, so you said that currently 1 in 10 supernova are being followed up on. And to my understanding, the main benefit of switching over to a machine learning method is speed, correct?
It would be, well, yeah,
Speed. So then, my curiosity is, what would the expected rate then be if we implemented a method similar to yours?
yeah, that constraint is mostly a result of the lack of just telescopes that we have to follow up. So the point that I was trying to get across with that is just that we want really accurate classifications so that we can pick out the interesting supernovae. So that's just sort of like why classification.
Okay, so you're not contributing to changing the rate, you're just helping to choose which ones.
Unfortunately, no.
Gotcha.
Yeah.
How big is your current data set of supernova, and then how big will the Pan-STARRS data set be?
Currently, it's about, I want to say, almost 200 supernovae. The Pan-STARRS data set, I'm still trying to figure out how to work with it, but I think it's going to be on the order of thousands, so it's going to be a lot better.
More questions for Adam? Oh, okay, so if not, let's thank Adam. Okay, our next student, Owen Day, advisor Federica Splotto, external leader Matthew Holman.
Hi everyone, my name is Owen Bay. I'm here to do about asteroid families and collision within our solar system. My advisor is Dr. Federica Splotto. Just for a quick project overview, the primary focus of this project is to use the information from the main asteroid belt to better understand the history of our solar system as well as how objects behave, which will in turn hopefully inform us on how other asteroid systems form. The biggest part of this project is identifying which asteroids are part of the same family and how old those families are. So there are two main models for how the asteroid belt formed within our solar system. The first one is that the belt started with many objects, and over time those objects were ejected from the belt, either going into deep space or becoming near-Earth asteroids. The other possible model is that the main asteroid belt started out empty, and over time objects came in from other places that involved gravitational effects. Based off of the results of this project, we should be able to figure out, or at least get a better idea of which one is true. If we find many asteroid families with old ages, we can assume that there were many objects in the belt to start off, and if not, we'll assume the opposite is true. The two red lines within that blue bar on this bottom graph are the youngest and the oldest asteroid family data set that I was able to work with. And so, a little spoiler, but we believe that it's going to be the asteroid families started, or sorry, the main asteroid belt started with more objects and lost them over time. The biggest phenomenon that makes calculating these asteroid family ages possible is the Yarkovsky effect. Put simply, the Yarkovsky effect is when light, in this case sunlight, hits an asteroid and the asteroid goes overheat, and after a small delay starts to re-radiate that heat, which is a small force on the asteroid. Depending on the asteroid's orbit, that can either slightly increase or decrease the asteroid's semi-major axis over the span of hundreds of millions of years. This is the primary way we're going to figure out how old these asteroid families are. as a quick overview so far, we have asteroids collide, create families, which is sort of in the one-done circle, and over a long period of time, those fragments sort of diverge, and they are either ejected into space or they're. So the first thing that we need to figure out for each of these objects that we can see through surveys is the diameter. We can't directly observe this precisely, but we can sort of extrapolate it from the absolute magnitude of each of these objects. So after we have the diameter, we still need to find the second major axis, which we can just find from the data sets of these surveys. So we'll plot each object in a family with proper second major axis on the bottom and the inverse diameter, and that sort of creates a V shape because the Yarkovsky effect has been pushing them apart. And we'll divide each of these. We'll divide this plot horizontally in bins with a roughly equal number of objects, and we'll take the leftmost for each to use as data points for a linear bin. We do get rid of a few of these data points. This is one such example where the red lines are sort of plot lines. Black circles are plots that are objects that we use in our line of estimate, and these red ones are ones that have been eliminated. The reason there are two lines is because we made one initially, and then the red dot was taken out, and we have a new line of estimate. To actually find the age calculation, we take those slopes that we just calculated, and we have that, we'll use that as our delta A. We still need to find the DABT, which is essentially your Yarkovsky calibration. It's this very long formula for which we need a bunch of values from the asteroid themselves. However, we can't directly measure these asteroid elements, so we use two different near-Earth asteroids for which we can actually observe things like their density, liquidity, eccentricity, and we'll use those for the calibration. Previous studies have used only Bennu, which is a B-type asteroid, and very recently we've been able to use Apophis data as well. These are two different types of asteroids, which we'll come into play later, but we'll be using both hand in hand when calculating our final results. So essentially we are sort of use this formula, and we'll be taking the slope and dividing it essentially by the DABT on the left side. So for example, for family 31, we find the standard errors are in the parentheses, but the actual values of the slopes are towards the left. Using the values in this table above, which are the best known values for the parameters that we have, we find that the ages calibrated through Bennu are roughly 753 million years old and 752 for the outer side. If we use the Apophis values, it's 1,345 million years and 1,343 million years old. The previous estimate for this family was 1,309 plus or minus 302 years, and we now have a much better standard error, which was one of the primary goals of this project. But also we can sort of tell that because the number value is much closer to the Apophis value, we sort of extrapolated that this asteroid family most likely has a composition closer to Apophis, which is an S-spectral type of asteroid. So for our conclusions, we can apply this method to basically every asteroid family that we've been able to observe. If we take other values and calculate their ages, we can see comparing to their previous estimates and what we would get if we were to calculate ages using Bennu or Apophis values. We can see that in this case, again, Apophis is likely the better estimate because it's simply closer to the known value. For a different family, which is 24, it would be much closer to Bennu. Again, Bennu's a B-type, so there's more carbon volatiles and excreting material actively, whereas Apophis is more stony minerally. But generally, our results do imply that the first model is correct instead of the one where asteroids are brought into the belt over time. And if this here theory is true, the amount of objects currently in our main asteroid belt would be less than 1% of that from the beginning of the solar system. And we also have a much better estimate of the Yarkovsky effect with the reduced secondary
asteroids which are the iron-rich type?
Iron-rich?
Which have families associated with them?
I haven't, so we use Bennu and Apophis because we had like good data concerning a lot of their properties. I'm not sure if there's an asteroid for which we could have like similar level of like accurate results. I'm not sure if it would be possible to like estimate based off of if it was farther like older or younger than Bennu or Apophis or somewhere in between. Like there's a certain threshold under which like it was in between that you could say like, oh, these asteroids are probably all of the same type, but I'm not sure how you like nail it down. You could say like, oh, that one's probably iron-rich or of that specific composition. We're just sort of like, because the values are much more similar to either Bennu or Apophis, sort of just like assigning them to the same estimate.
So how do you really know that there's this set of asteroids that all belong to the family? How does that?
So when they collide, when the asteroids collide, their orbits are sometimes they fragment, and sometimes one asteroid is much larger than the other one, so it doesn't have much of an effect. But every object that was part of the collision will have a related orbit after that, and then like the V-shaped graph isn't necessarily like an actual graph of like the objects and how they spread out. It's just the size essentially, or the I guess the inverse of the size on the y-axis, and then semi-major axis.
Yeah. But I guess I'm just wondering, how are these families identified? Is it that they have the same composition, or that you run their orbits back in time and you see they all originate from a
I
common
didn't
body?
delve super into the survey data itself, but I would imagine it's just the orbits, because we are the biggest source of error in previous estimates is the fact that we still can't directly observe any of these objects, which is why we have to extrapolate the diameter through like the magnitude and all the
More questions for Owen? Okay, if not, let's thank Owen. Our next student, Marina Stefanoni, advisor Federica Spoto, external reader Matthew Payne.
I'm Marina, and I was looking at the first steps in helping to refine the automation of preliminary orbital determination using asteroids 2023 RS and 2023 UJ7. My advisor was Federica Spoto. So first, I was working with Minor Planet Center data, and this is the only center worldwide location in the world that people send their observations to. So they get millions of observations per month. A lot of these are near-Earth asteroid observations, and these are of special interest because the Minor Planet Center works with NASA on planetary defense. And so the Minor Planet Center is responsible for the identification, the orbital determination, and designation of all of these objects. And as of now, the observation to designation process is not entirely automated. And so the project focus for me was to look at helping the automation of orbital determination. And this is an example of how they receive observations, where it's an 80-column format with celestial coordinates, magnitude, and observatory code. So different observers can send in their observations of the same object. So the project overview is I was trying to understand and test a software that takes in these observations and then determines the preliminary orbits. And the goal is to reduce bias, error, and to help make quicker designations. So I did this using two near-Earth asteroids, 2023 RS and 2023 UJ7. So the first object had a very close encounter with Earth in September. It's a very small and quickly moving object. So because it had such a close encounter, we had a lot of observations. 33 in a span of 7 hours and 40 minutes. And these are some of the orbital elements and characteristics of this object. And the second object also had a close encounter, but not nearly as close as the previous object. And so we only had 12 observations, and this was spread across 3 separate days from multiple observatories. This was also a slower moving object and larger, and so we chose to look at both of these. First, because they were already designated, so we could compare our results to the orbital elements that we have in the Minor Planet Center database. And also, we wanted to compare the results of looking at a more normal or typical object that's larger and further away versus a very close, quickly moving near-Earth asteroid. And so first, the orbital determination methods. We used 3 different methods, Gauss, degree 8 polynomial solutions, or Laplace. And these functioned differently based on the geometry of observations. So essentially, if you had some observations that were more spread out in time evenly, certain methods could batch the observations better and produce an orbit. So there are some cases in which, for example, Gauss was not able to produce an orbit, however the Laplace method could. So that's why we had multiple methods, just based on the geometry of these observations. And so the way we looked at the data through the code was that for each of the objects, we would batch the data looking at different times between the first and last observations. And so just a simple way to put it is looking at the first 4 observations, for example, for 2023 RS, and then adding an observation each time, obviously increasing the time with each observation, and then looking at whether or not we could produce a preliminary orbit. And same for the other object. And so running through the code, essentially, first you would try to acquire the orbital elements. So this would initiate the determination process. And I would just run this top down, so through Gauss versus degree 8 versus Laplace. And the order of this didn't matter. It's just I wanted to find one method that could produce an orbit, and then with that orbit, we would run a least squares minimization process. And this is used to help improve the preliminary orbit when we're not able to add more observations. Yeah, and the output of the code is orbital elements we looked at were semi-major axis, eccentricity, perihelion distance, and then the uncertainty of these elements. And so the results of increasing time, or the observations for these objects, was that obviously, as you can see, as more time increased between the first and last observation, these red lines on both correspond to the true semi-major axis value that we have in the database, and then the data points are the results of the preliminary determinations. And so as there's more time between the first and last observations, the data points get closer to this red line. And from here, looking at the first time that the observations sort of drift towards this red line, I noted those observations and wanted to look at the error associated with the preliminary orbits. So for 2023 RS, looking sort of at 0.11 days, and then for the second object, around 4.25, those became close to the red lines. And so those corresponded to, these graphs are plotting the element over their uncertainty. So we're looking at the threshold of 3 sigma. So that's what the red line and blue dashed line correspond to. So the moment that the ratio crosses that line is when we say that we have a pretty good orbit, that the uncertainty is not so large. But the orbits that have an uncertainty that's too great, we would, even if there's an orbit that's produced, we would not take that as our preliminary orbit. And so for 2023 RS, since that's the closer, faster, near-Earth asteroid, that was of special interest. So we looked at that after the 13th observation, more or less, we could probably have used the preliminary orbit. And so the key takeaways, and this is Earth's orbit, and this is 2023 RS, and this just shows how quickly we can have we found out that both objects could have been designated sooner than they were. 2023 RS could have been designated after the 13th observation with this preliminary orbit with less uncertainty. And the whole encounter took 33 observations, which was about 7 hours. So the difference between 2 hours and 7 hours and 42 minutes is quite significant, especially when an object is moving so quickly. And we're first able to detect it when it's very close to Earth. Because the goal would be to have an automation process that can designate these objects quickly enough that if there's a potential for impact, then we would know in advance and hopefully be able to do something about it. And so future work would be to test more near-Earth asteroids, because obviously I only ran with 2, and run a robust statistical analysis. Also, it would be interesting to find a specific threshold time for which objects can be designated, so sort of a universal time that if there is this range between the first and last observation, then we know that we could produce an orbit. And then also to save time, which orbital determination method works best given some geometry. We haven't looked into this, but it would be useful to not have to run through all 3 if the last one happens to be the one that works better with this geometry. And lastly, I'd like to acknowledge my advisor, Federica Spoto, who can't be here. She was awesome. I learned a lot. It's been really great working with her. External reader, Matthew Payne, thank you for the comments. Minor Planet Center provided the code and then the data that we worked with. And then lastly, thank you to Professor Chen and my classmates for staying here for the past few hours. Really appreciate it.
Question for Marina?
So we're all looking forward to the LSST, which is going to detect a lot of objects. The LSST has a fairly rigid program. It doesn't adjust its schedule because there's an interesting asteroid there. Whereas I think with the current system, if you pick up a near-Earth asteroid, everybody else tries to make sure they get some data on it every night.
Yeah, I'm not sure how, with the data that we were working with, it's coming from many different observatories. So obviously if there's a very close encounter, hopefully there'd be multiple observatories that can observe it, send in the data, and then we have more data to work with. Hence why we had 33 observations for this object versus the other object, which had fewer. But it would be ideal to have sort of a very quickly updated uniform database on super close encounters.
Well, most of the people in LSST will pay that service, it's just noise against them in the way. But some people love asteroids still.
So I'm just curious, so these objects that you were studying, they were just identified. How long after they were identified did they go through closest approach to the Earth? I mean, are we finding them 5 hours before closest approach?
So 2023 RS, the very close one, its closest approach was on the 11th, I think. No, its closest approach was on the 7th. Sorry, that's not right.
Yeah.
With the video that didn't play, it showed that, so the first observation that they found was at the beginning of September 7th, and then it was a few hours later that it was at its closest approach.
Okay.
So it's very, very quick. That's what I was trying to show with the video. It's a very, very quick time scale. Hence why it's so important to have an automated, efficient process.
And then what, do we have an estimate of the mass of these guys?
I know that the roughly 2023 RS, the smaller, moving very quickly, I think it was about estimated to be like 3 yards in diameter. So I don't really know what that corresponds to.
3 yards?
Yeah,
Okay.
so quite small.
Right.
And then the other object was more typical and it's about 60 yards across.
Okay, that's bad.
Yeah, but that was way that way. That was much further away, yeah.
Any other question? Yeah.
Can you go to the slide where you were like converging on the values and comparing to the high-flying centers? Yeah, yeah. No. So like on the left plot, it seems like you're converging to a value that's slightly above what the minor planetary center's value is. And I'm wondering, is the difference between your 2 values enough that it would like totally knock off the orbit enough that it like wouldn't be a near Earth impact anymore? Like how significant is that difference, and would that difference be enough to maybe invalidate your process, or is that not significant enough error?
I did not look at what that error is. However, that would be important to look at, because obviously if it's a very, very close encounter and then the semi-major axis is off by anything significant, then that can certainly be messed up. But also there, I assume with the orbit that we determined preliminarily, there is an error, like an intrinsic error that we're going to assume. So if it's anywhere close, even if it says, okay, it's going to miss us by like a few kilometers, or not a few kilometers, like 100 kilometers or whatever, then that would still be worrisome. So I think there would be some notification type situation. Casey?
Just trying to have more like context on like how bad it would be if they hit like a 3-yard like across meteor, assuming that all the kinetic energy got there. Would that be like, you know, like a small nuclear warhead going off, or like what are we talking
You're
about?
asking me, I don't know.
No? Okay.
Well, Meteor Crater in Arizona was what, 50 meters across? So you ever seen Meteor Crater? It's a 1 mile.
Yeah, big hole, yeah.
Yeah.
Not pleasant to be around at the time. Now, probably better.
But something that was 3 meters across might mostly break up before it gets in. I don't really know. Depends on obviously composition, structural readiness, and metallic is much less likely to break up.
Yeah, that's also the problem, is that because the encounter is so close and because the object is so small, it's difficult to pass the closest encounter, it's difficult to still observe it, and so you can't really get information on what the composition is as well.
Any more questions? Okay, if not, let's thank Marina. Okay, so this will conclude our junior thesis presentation. Let's congratulate our students for successfully completing their research projects and for the nice presentation. All right.
Thank you. Thank you, everyone, for coming.
Always good to see you on the end of this.
Yeah,
we get back to 7 hours programs for your
back-to-back
Yeah, I just got like that. It's like, ooh, let's take it.
Yeah, but I'll be done. Not yet. I need them.
Is it actually like or is it like?
And I think it was.
I think I jumped right into that.
Thank you for coming. Just in case.
It's just with this
Okay.
now I heard this guy on Tuesday.
Yeah, right. We're gonna dial it. I thought you got ours tomorrow. That's weird. 10:30, is that right? Awesome. All right, perfect. I'll see you then.
All right, that was great. Well, thanks.
Oh my god. Oh yeah, your friends. Yeah, that
So
was so cute.
That was bad.
I took extra one in sophomore year.
Oh, right.
Do you want me to take you to Columbia?
Yeah.
So wait, you took it.
Yes, I.
Yeah, you should have a 0.5.
Okay.
2 years.
Yeah. Okay, that's I 1, 2, 3. Take a few more. And maybe different angle.
Right?
All right.
Wait, take a selfie.
Yeah.
Yeah, 0.5.
wonderful GR class as well.
Yeah, no,
I enjoyed the double.
the GR class is just, I mean, this was fun, but the GR class gave me a different class I think, so I think you may have, yeah, you may have